Hey there, everybody. Welcome back. This is 13.6 in Anton's Calculus Early Transcendentals, 11th edition, Calculus 3 at College of the Sequoias in fall 2022. 13.6 is on the directional derivatives, which is effectively the section on the gradient. So let's just jump right into it. In the last section, we learned about, well, in the last few sections, we've talked about partial derivatives. We could take it with respect to X, Y, or Z, and they all represent rates of change along coordinate axes. It was parallel to the x-axis or y-axis or z-axis. It's so basic. But what about rates of changes in other directions? Well, this is where we can start stepping it up a notch. We're going to make a unit vector, u. We're going to start at x naught, y naught. We'll head in the direction of xy. So xy minus x naught is going to be some arc length times that unit vector u1, u2. We got a nice little picture here, arc length along there. And then this is along some surface z. The slope of the tangent line in the u direction at x naught, y naught can be expressed as a rate of change with respect to x. And when we do that, we call it the derivative in the direction of u, rather than along the coordinate axes. And our book uses capital D with a subscripted u vector. And we'll stick with that pattern. So the directional derivative in the direction of u at f of x naught, y naught, it's the slope of the surface z in that direction. So like it's a lot, we're doing a lot of talky. Let's look at an example. So we've got f of xy equals x cubed minus 3xy plus 4y squared. We'll go in the direction where theta is pi over 6. So u is root 3 over 2 and 1/2 for x and y. And we'll start at the point x naught, y naught being 1/2. And then we'll find the directional derivative in the direction of root 3 over 2 and 1 over 2 at the point 1, 2. Okay, so we're starting at 1, 2. We're taking a vector in the direction of u, root 3 over 2, 1/2, and we're going to find what the directional that tangent is. So we have to take the derivative du is the derivative with respect to arc length of the function. We're going to do f of x naught plus su1 and y naught plus su2. And it can get pretty tedious. So we're plugging in x naught plus su1 for everything in x and y naught plus su2 for everything for y. And it gets a little ugly. I didn't multiply everything out. I just started taking derivatives with respect to x or s. Remember, this is, well, the way I have it written, maybe, well, x naught and u1 are all values. They're not variables, okay? Those are actual values at that point. I just haven't plugged them in yet. I could plug in 1, 2 and root 3 over 2, 1/2, but I think it's easier to keep the numbers out of it for now. We take the derivative with respect to s. We get that. That's when I plug it in and start cleaning up from there. So we have this value, that's our directional derivative, and we're taking the value of the derivative of it at s equals 0. Okay, which means it's the tangent point or the tangent vector at that point, so there's no arc length there. And we get it's approximately 3.9. It's negative 3 root 3 over 2 plus 13 over 2. This is pretty tedious. There is an easier way. And that's where gradients come in for the next video. Peace.